Okay, we're going to wrap up section 11.2 by talking about the limit laws again and discuss the divergence test. So to really think about the convergence of a series, remember that we say a series of a sub n converges if and only if the sequence of partial sums converges. So in that sense, because we're really just talking about the sequence of partial sums and we have the tools and ability to convert some of the limit laws from the sequence section to series, then we're going to get some nice results here. I do have to warn you, not all of them carry over. And that's because S sub n is a special kind of sequence that depends on A sub n. So let's talk about the limit laws for series. So we're going to suppose that we have two convergent series, which we're going to call, we're going to index their, we're going to label their terms both A and B, and then the limits of the series are going to be A and B. So they're going to converge to A and B. And we get three laws here, which is that the series composed of adding up the terms term-wise, right? So A1 plus B1, A2 plus B2, and so on, is what we would expect. It's A plus B. Something similar happens for the difference. And lastly, if we're going to just multiply each term by C, a constant, then we multiply the sum by C. However, notice we can't say anything about whether the series A sub n times B sub n or the series that comes from dividing A sub n by B sub n. We really can't say anything about the convergence there. And the reason for this is when you combine the notion of partial sums with multiplication and division, things don't work out the way that you want them to. All right, so not to overstate how important this is, but we're laying the groundwork for basically the entire rest of the chapter. And all the things that we're discussing up until this point are just for us to be able to determine whether a series converges or diverges. And so we're going to start with a first consequence, which is the divergence test. And before we get to that, we have a first consequence, right? So we can call this a lemma. We can call it basically like a step on the road to showing the full divergence test. So our claim, which is not the divergence test itself, so it's an intermediate step, right? I'm going to do an aside here. If the series converges, then the limit of the terms of the sequence, right? So just the terms of the series, not the partial sums, is 0. Okay, why must this be true? It helps to think about the contrapositive, right? What happens when the limit is not 0? So there's two cases here really that we want to talk about, right? So the first case is if this limit of the terms is some capital A, which is not equal to 0, right? So basically think of all the terms are getting closer and closer to 1, for instance, right? In this case, eventually we add copies of over and over again. So in other words, the series, if we expand it out term-wise, right, it'd be a sub 1 plus a sub 2 plus that, plus eventually, it's going to be very close. I should put approximating equals. So it's not equals, it's approximately equal to a plus a plus a plus a plus etc. forever, right? So you get something that's basically infinitely many copies of A. And whether it's positive or negative, it's just going to explode. It's going to diverge. So intuitively, that makes sense, right? Case 2 is the limit in which, the limit doesn't exist. So it'll either bounce back and forth between two values, or it just completely explodes into larger and larger values. The sequence never settles on a value, right? And in this case, we guarantee nothing except the sum diverges. So really what this is stating is basically we're justifying by thinking about the contrapositive, which is if this is not true, then this is not true. And the real divergence test is the statement, if the limit as n approaches infinity of a sub n does not exist or is not equal to 0, then the series diverges. Now this is a divergence test, it's not a convergence test, so you can't say anything conclusively about whether the series converges, just that the test diverges. So for instance, so two consequences, right? So one note is the converse is not true. So because a sub n equals 1 over n converges to 0, but the series 1 over n diverges. We saw that already, right? So you can't, just because the limit goes to 0 doesn't mean that the series converges. 2, it's powerful for when we suspect a series diverges and we just want to say, okay, it's definitely not going to converge, right? Used for showing divergence. Which it sounds like, okay, well, you either have convergence or divergence. So how can you say, it can only show divergence? It's because just because you can show divergence doesn't mean that the test can't be inconclusive, right? So in other words, if the limit does equal to 0, as we saw here, right, there are different cases, and so we're not guaranteed anything. And so you can only really use it for if we suspect something diverges, we can then conclusively show that it does. And that's all. So in the set of videos for the next few sections, we're going to apply these ideas and more broadly talk about when they apply, what they say, right? And some tips and tricks for really effectively using these new tools for testing divergence or convergence.